Hey everybody. Of all the videos I was gonna make, I've been kind of most afraid of this particular one. Um, because this particular one is very, how should I say it? People are bad at long division and people are bad at doing this. But I still want people to be able to do it. This is a skill that comes up a lot in Math 101. Um, and like I said in the previous one, this is actually a basic skill that gets used in a lot of different types of mathematics, not just in terms of fractions, or in this case, rationals. So let's get going. We're going to be talking about turning improper rational expressions into mixed rational expressions. Doing it the other way just involves multiplication, making sure the denominators are the same, and then expanding and simplifying. Doing it backwards is bonkers. So we're going to talk about how to do it, and it's not too tricky a skill to pick up in practice, but there are a lot of things people get wrong, and I want you to be able to do it right. So wish me luck explaining this. The learning objectives in this is I want you to be able to use polynomial long division, that's what I'm going to teach you today, to partially factor a polynomial. I want you to interpret the relationship between divisor, dividend, quotient, and remainder. Those should all be friendly words from your childhood, in terms of multiplication and division, both. And finally, I want you to use polynomial long division to turn an improper rational into a mixed rational. Okay, let's talk about how to do that by introducing our friends, fractions. Okay, so long story short, 3 plus 1 over 4 is the same as 13 over 4. Okay. One of these is a mixed fraction, and the other is a improper. And the way to tell in terms of fractions is if the numerator is bigger than the denominator, it's improper, and you can rewrite it as a mixed form. So last video, we talked about how to go this way. And the way to do it involves multiplication, right? And so in this case, you'd write 3 times 4 over 4 plus 1 over 4, which gives you 12 over 4, plus 1 over 4, which gives you 12 plus 1 over 4, which gives you 13 over 4. Fine. It's actually fairly easy to do it that way, and it's easy to do it with polynomials as well. You know how to expand a polynomial. All we need to do is compare the denominators and make sure they match before we add them together. The question we're going to ask in today's video is, how do you go that way? So how did we do this with fractions? We used a procedure called called long division. Okay. So to review, 6, 5, 2, 5. Here's a big honkin' super terrible fraction, and I want to write it as a mixed number. How do we do it? We used long division. Okay, so long story short, we take this number here and we write it over here. Long division is an algorithm. We've known it for thousands of years. It's been passed from one culture to the next. Then you write this number over underneath the bench. 1, 6, 5, 2, 5. Okay? And then the next step is you're going to break this into columns. Oh, I don't like that color scheme. It's gross. You call this number the divisor, and you call this number down here the dividend. The divisor is the number that you're dividing by. It's the number in the denominator, and the dividend is the number in the numerator. It's That's the number you are dividing, cutting into pieces. Okay, so long division as an algorithm isn't too tricky. The goal here is I'm going to try to cancel out the dividend piece by piece, starting from the left-hand side. And I'm going to do it using multiplication. In essence, I'm going to write numbers up here and then multiply these two numbers together down here, 3 times a, and I'm going to do it in such a way that the number you get when you subtract those two values, this number here, I'll call it b, this number here, you want to make it less than 3. So you want to choose this number to be as large as possible where this number is still less than that number. Okay, so let's back this truck up. Beep, boop, 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 boop. Boop, 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 beep, 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 beep. Okay, so you start in this column. There's nothing I can multiply 3 by to make it larger, that gives you a number smaller than 1. So I'll write a 0 there. 0 means just ignore it for now. Okay, so then I'm going to fill in this column. 16. What's the largest number I can get by multiplying 3 that isn't bigger? What's the largest multiple that's smaller than 16? It's 15. So I'll write 5, and then 3 times 5. 3 times 5 is 15. And I'll write a subtraction sign, and then I'll subtract these two numbers. 1, and now I copy these numbers down this part of the column. And now I'm going to try to cancel out the 15 here. I can do it with a 5. 5 times 3 is 15. These two cancel out completely, which is great. And now I carry these two down to 5. What number do I multiply 3 by to make it smaller than 2? There's no number, so I'll write a 0. And so 0 here. 2 minus 0 is 2. 5. And then what's the largest number I can multiply? Let's see. 24 is smaller than 25. So I'll write an 8. 8 times 3 is 24. 1. The result is two numbers. There's this number up top and this number in the bottom. Okay? Each of these have a name. This one's called the quotient, and this one's called the remainder. Okay? And so we say that this number over here, 16525 divided by 3, is equal to the quotient 5508 plus, oh, that's next, 08 plus the remainder divided by the divisor. Okay. And I can calculate them both. Let's see, 16525 divided by 3 on my calculator is 5508.3 repeating. 5508 plus 1 divided by 3 is 5508.3 repeating. These are definitely the same number, and that's the point. So long division allows me to rewrite this improper fraction in terms of this mixed number. And that's the idea. Sometimes when I want to write these relationships, I would write 16525. So that's the quotient. No, that's the dividend divided by 3, which is the divisor. It's equal to the quotient, which is, oops, 5508. That's the quotient. Big R, that means remainder, 1. Remainder. Okay? That said, I'm never gonna write that. And just to jog your memory. Okay. So a lot of people have trouble with long division because they don't know what it's doing or where it comes from. As an algorithm, it doesn't make sense to them. It's just a series of steps that you follow. That's certainly how I learned it. But there is an idea behind this, and it's actually a pretty useful idea. You're actually performing an operation. So let's talk about where the long division algorithm comes from before I teach you polynomial long division. Polynomial long division is an algorithm that works in exactly the same way as numerical long division. And so I want you to be comfortable with the ideas of numerical long division before we get into polynomial long division. So the question is, where does division come from? Where does this procedure come from? Why do we do it? It's like I said, we discovered, various cultures have discovered long division thousands and thousands of years ago. It predates algebra. And in essence, the idea is this. Somebody gives you a number. Wait, hold on. Yep. Somebody gives you a number, and they ask you to divide it by 3. What does that mean? Like operationally, like we can do the calculation, but what does it mean to divide something by 3? Let's imagine. I have 424 Lego bricks. Right? They're all the same size. And then I have 3 children. A, B, and C. I'm not very original when I name children, which is why nobody will let me have children. But I have 3 children, and I want to divide this pile of bricks evenly among the children. So each of my kids are going on a voyage. They're never going to see each other again. I want to give them some Lego, but I want it to be fair. So I want each pile of bricks to have as many bricks as possible, but I want all of the piles to have the same number. How do I do that? This is why we call division. We're splitting something up. Well, here's my pile of Lego bricks. It's a big pile. Okay. It's got lots and lots of bricks in it. What I would do is, the easiest way to divide this among them is to just do it the old-fashioned cowboy way, where you say, okay, this one, actually, you know what? I'm going to use the lasso. Hold on. You take them one piece at a time. You go, this one goes to A, and this one goes, whoa, hold on, and this one goes to B, and this one goes, ooh, come on, be nice. All right. And this one goes to C, and then this one goes to A. One for you, one for you, one for you. And just to do that over and over and over until all of the bricks have been accounted for. And it's entirely possible that at the end of this procedure, you have a brick left. A brick remaining. Or you might have 2 bricks remaining. Is it possible for there to be 3 bricks remaining at the end of this? No, because if there were 3 bricks remaining, you would divide these last 3 among them. So you're gonna divide them up until the pile of bricks is less than 3. Okay? And the result then is you have 3 evenly sized piles, and I want to know how big each pile is. So I want to know how many bricks each kid has. Does that make sense as a procedure? One for you, one for you, one for you. One for you, one for you, one for you, until they're all doled out except for some remaining ones. And then, yeah. And I want to know how many bricks there are in each of these evenly divided piles. That's what it means to divide something up between them. Okay, so this is actually, it works. You see it in old cowboy movies. People are like, hey, divvy up this gold that we just stole from the train. Here's the thing about it. it's not a very time efficient way of divvying things up. It works and it's fair and it makes sense. And if it makes sense to you, I hope you're happy because that's great. But it's not very time effective. A much more efficient use of time is actually to take your kids and to tell them to sort the blocks first. And by sort the blocks, I mean take your big pile of bricks and connect them together. I want you to connect them together into patterns. I want you to take as many as you can and make slots of 100. So you connect 100 bricks in there, you get the nice nice sheet of bricks. Each of these sheets has 100 bricks in it. And to keep doing it. Okay? How many sheets of 100 will you get? Well, it's 400, so you get 4, right? And then, so the kids will say, well, there's not enough bricks left to make another sheet. And you say, okay, well, now make sheets of 10. So these ones are all sheets of 100. These are all sheets of 10. And they do it until, well, they don't have enough to make another sheet of 10. How many remaining are there? Well, there's 4 bricks remaining. That's what it means to have 424 bricks, kids. Great. Fantastic. So now, the idea here is you're going to dole out, in the same way as we did before, one for you, one for you, one for you, each of these bricks. So we're going to say, okay, this brick goes to you, and this brick goes to you, and this sheet of bricks goes to you. Anyway, right? We'll just divvy them out the same way we did before, but now instead of having to do it 424 times, I only do it like a few. Does that make sense to you? So that's a procedure that takes a little bit less time. It's less time intensive, and it makes sense to do it this quickly. So let's talk about long division. According to long division, I should be setting up 3, 4, 2, 4. Okay? So I'm going to show you both procedures at the same time, and what you'll see is the procedure for divvying up bricks is exactly the same whether or not you're doing it with Lego bricks or in these stacks of 100, or you're doing it in you're doing long division numerically. Okay, so let's start with the sheets of 100. First you go, okay, well, each of you get a sheet. 1, 2, 3. And you do it until the pile that remains of 100s is less than 3. So I can't divvy this one up evenly among them. So how many sheets of 100 does each person get? That's essentially me asking, okay, well, for each sheet that each person gets, there's going to be 3 times that number in total. So I'm divvying up that sheet of 4 into 1 apiece. 1 times 3 is 3. And that leaves me with 1 sheet of 100 remaining. Now I can't divvy that up among them, but what I can do is break this sheet into sheets of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? How many sheets of 10 are there now? There are 12 sheets of 10, and I can divide these strips of 10 up among my 3 children. So I go, there's 1 for you, and 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 1 more for you, and 1 more for you, and 1 more for you. Okay? Essentially, I'm asking the same thing. I want to divvy them up among my children until I end up with a pile that's less than 3. Which comes down to me saying, hey, how many does each get? So each gets, you multiply it, there are 3 sets of them, so it's 3 times that number. You want that number to be less than, in this case, 12. That number's 4. Each get 4. 4 times 3 is 12, minus 12, 0, 4. What remains then are these single ones, and I can divvy those up. How much does each child get? This one goes... Oops, sorry. Oh no, well, each one gets 1, and then 1 remains, which is equivalent to us going, each one gets 1, so that's 3 in total, 1 remains. You see? And so this idea of breaking my overall Lego pieces into pallets and strips and single units, and then divvying up the pallets, strips, and single units is exactly equivalent to, I mean, it's literally the narration for what we're doing when we do long division. So our long division algorithm is just this procedure. And so it's actually faster to do it with numbers, calculation-wise, than to divvy things up. But essentially, that's all it comes down to. Okay. So... I mentioned earlier that anytime you do this, we're talking about the relationship between 4 different numbers. You can think of these as the 2 numbers we started out with, and then the 2 numbers we ended up with. But essentially, there's 2 different ways we can talk about this. So to review, when you're doing long division, it's divisor. Under the thing, it's dividend. Up top here, that number is called the quotient. And then when everything is done, the number down here is called the remainder. Okay. In terms of division, the relationship between these numbers is this. Dividend divided by divisor is equal to the quotient plus the remainder divided by the divisor. Okay? Or alternatively put, dividend divided by divisor is equal to the quotient remainder remainder. Okay? So we can write their division relationship in 2 different ways. There's also a multiplication relationship between the 2. The multiplication relationship between the 2 is actually kind of obvious. Let's see. I have drawn circles all over this. Give me a second to clean this up a little bit so you can talk about... Oh no. Okay. So, in terms of Lego blocks, and let's see, there was one remaining. There's a total number of Lego blocks. There is the number of groups I'm splitting it into, right? There is the number of blocks each individual gets. And there is whatever's left behind. Okay. So in terms of numbers, we call the total the divisor. We call the number in each pile the quotient. We call the number of groups the... Ooh, wait, hold on, I made a mistake. We call the total the dividend. I never use these words. These are like words from when you're a little kid. I've forgotten them all. Dividend. The number of groups is the divisor, and the number left behind is the remainder. Okay? And I'm only spelling this out because we can then ask the question, how many blocks do you have in total? Well, the number of blocks you have in total is the number in each pile times the number of piles plus the number left behind, right? And that means that we can rewrite this as dividend is equal to the quotient, which is the number of blocks in each pile, times the divisor, which is the number of piles, plus the remainder. Okay? So let me do an example just demonstrating that these two relationships are true. I'm going to focus on these two relationships. Boop and boop. Okay. So for example, 1731 divided by 14. 14 divided by 1731. So start off in this column. 17, so that's 1 minus 14 is 33. That's probably 2 minus 28. 51. 3. So that's 342. And the remainder is 9. Okay? So the dividend is 1731. The divisor is 14. The quotient is 123. And the remainder is equal to 9. Okay? Now for the fun part. Let's combine them all like this. So the quotient is 123. The divisor is 14 plus 9. What's that equal to? What? 123 times 14 plus 9. 1731. Hooray! It's the same number. Okay, you see? In other words, we're talking about the relationship between four numbers here. You start out with the quotient, you start out with the dividend and the divisor, the numerator and the denominator, and then you end up with two new numbers, the quotient and the remainder. And these four numbers can be written in a division relationship, but they can also be written in a multiplication relationship. And that's going to come up a little bit later. Okay. Now it's time to learn polynomial long division. Okay, so polynomial long division, you start out with a rational expression. That means that it's a it's an expression like that. It's a polynomial divided by another polynomial. The one on top is the dividend, and the one on the bottom is called the divisor. Okay? So here's how it's going to work. You're going to lay these out in long division exactly the same way as you did before. The divisor goes out front, and then the dividend goes under here. Write it in decreasing order of power. Like that. Okay? So we're going to break this up. Instead of decimal digits, we're going to break it up in terms of these individual terms being added together in the polynomial. And the idea is there is some kind of polynomial. This numerator here, or sorry, this quotient here, this will be a polynomial instead of a number. So the operation of this is exactly the same. The idea is term by term, we're going to try to cancel out these expressions by writing other terms up here. Okay? So the idea here is I'm going to write down a number up here, like 4x. And then I'm going to multiply this expression with this expression to get another polynomial that I'll write down here, and then I will subtract the two. And the purpose here is that I want to cancel out that one there. Does that make sense? Okay. So we'll do our best. So what expression do I need to do? So I'm going to use this term to cancel out this term. What do I need to multiply 4x by to make it equal to 28x squared? I need to multiply it by 7x. So I multiply it by 7x, and I get, so 7x times 4x is 28x squared. Put it in parentheses. And then 7x times 2x is 14x. And now I'm going to subtract these two polynomials from each other. This first term is 0, and the second term gives me minus 2x. I'm going to copy this one down, minus 4, and repeat the process. What do I need to multiply this term by to cancel out that term? Well, it's negative. So I need to multiply this number by something to make it equal to that number. How about minus a half? So I do that. 0.5 minus 0.5 times 4 is minus 2x. 2 times minus 0.5 is minus 1. And now I'm going to subtract these two polynomials, and the first will cancel out just like I want, and the second will give me something new. Okay. So that is, in a nutshell, what polynomial long division is. It follows long division in exactly the same way, but the results aren't two numbers. It's not a quotient and a remainder. Instead of a quotient number, you get a quotient polynomial. And instead of a remainder number, you get a remainder polynomial. But the idea here is that after you've done this, the relationship dividend is equal to divisor times quotient plus remainder should still be true. That's how this algorithm works. So let's test it. The divisor is 4x plus 2. The quotient is 7x minus 0.5. And the remainder is minus 3. Let's expand this out. So it's 4x times 7x minus 0.5 plus 2 times 7x minus 0.5 minus 3. So that's 28x squared minus 2x plus 14x minus 1 minus 3, which is equal to 28x squared plus 12x minus 4. It's the same thing. They are the same. That's the purpose of this expression, is that what we're doing in the end is we're rewriting our original polynomial in terms of a partial factoring. It's not completely factoring it, but I'm writing it in terms of two polynomials that are multiplied together plus a third polynomial. Okay? just like in the exercises we've been doing at the very start. This is essentially taking expansion and doing it backwards. Okay, so what was the point to all this? The point was that I wanted to be able to rewrite my improper rational in terms of being a mixed rational. How do I do that? Well, hold on. I'm going to recopy. Maybe I shouldn't recopy. You know what? I'm going to just copy and paste. Come on down. Come on down the page. Okay. So, this is the polynomial I started with. It's the rational I started with. Okay? And this here is the relationship. It's the relationship I discovered by doing long division. Okay? How do I take this relationship I just discovered? What's all that work I did? How do I turn that into something that's compared to that? Well, to start off, is this expression the same as this expression? The answer is no, they're not the same. This is a rational. It's one polynomial divided by another polynomial. This expression here is just a polynomial. It's not being divided by anything. How do I make this expression down here the same as the one up top? The answer is I just have to divide it by another polynomial. So what I'm going to do is I'm going to divide both sides by 4x plus 2. 4x plus 2. Now this expression is the same as the original one. I can rearrange this expression, however. I can write it as two pieces. 4x plus 2 times x 0.5 divided by 4x plus 2 minus 3 4x plus 2. And then I can cancel these two. And what leaves behind is 7x minus 0.5 minus 3. A nice mixed rational expression. And the idea here is polynomial long division has let me rewrite my original improper rational as a mixed rational expression. What's the relationship here? The relationship is dividend divided by divisor is equal to quotient plus remainder divided by divisor. Okay, so let's try it once or twice until we get the hang of it. 8x cubed plus 4x squared plus 2 divided by 2x squared plus 1. What do you do in this case? You know what? I'm going to actually take a big step back. I'm going to try a slightly simpler example. I think you need to see just another example of the same one we started with. Okay, so how about Oh, no. Wait, hold on. Sorry. I'm doing this on the fly. Most of these things are scripted, but I can't find my original thing. Okay, how about this one is x squared hey, right. It's not ready. Oh, it's an eraser. Hold on. Okay, so x squared plus 2 all divided by x minus 1. Okay, let's try this one. So the way it works is we need to start by writing out the long division sign. Okay, so this one I'll write out as x minus 1. How do I display the numerator underneath? In the very first exercise, I was asking you about polynomials like this, and I was asking you find a0, find a1, find a2. And if it was missing a term, so this one's missing the a1 term, the first order term, I was explaining that you could write these with a 0 coefficient. And that the coefficient, the term should be there, but it had a coefficient of 0, so it wasn't showing up. When you're doing long division, you want to count down from the highest. 2, 1, 0. Okay? So you want all the terms to be present for the reason, for spacing reasons. And then, let's start. What do I need to multiply x by to make it the same as x squared? I need to multiply it by x. Where am I going to put it? I'm going to put it to the x in the... Alright, so in these columns, this is the x to the power 2 column, x to the power 1 column, x to the power 0 column. I'm going to put the first term in the x to the power 1 column. And then I write out x to the power 1 times this expression. So it's x squared minus x. And now I'm going to subtract them. Be really careful about signs. So these two cancel out just like I wanted. And these two add together in a fun way, and you get plus x, and then you copy things down. Plus 2. So what do I need to multiply this x by to make it cancel out with that x? I need to multiply it by 1. So plus 1, and now I multiply them, so it's x minus 1, and now I subtract them. Plus 3. So the result is that the quotient is this polynomial and the remainder is this polynomial. So x squared plus 2 over x minus 1 should, according to this, be rewritten x plus 1 plus 3 over x minus 1. Let's confirm by trying it with a number. Try it when x is equal to 2. The top here becomes 2 squared plus 2 over 2 minus 1, so that's equal to 4 plus 2 over 1, so that's equal to 6 over 1. And the right-hand side is 2 plus 1 plus 3 over 2 minus 1. So that's 3 plus 3 over 1, so that's 6 over 1. They both value 6. So they're the same. Does that make sense? All right. So let's try a more advanced question. The one I had prepared for you. Eight x cubed plus 4x squared plus 2 over 2x squared plus 1. I'm going to write them out with all of their missing, so zero coefficient terms. So 2x squared plus 0x plus 1, and under here 8x cubed plus 4x squared plus 0 times x plus 2. And this splits it up into columns, which I can then sort my answer by. So what do I need to multiply this by to cancel out that term? 4x, right? So where does 4x go? It goes in the x to the power 1 column. And now I multiply this polynomial by this, and I write it on this line. So it's 4x cubed plus 0x squared plus 4x. And now I subtract. It's supposed to be an 8. I got 4 crazy. Okay, good. So these two subtracted to 0. These two subtracted are 4x squared. And these two subtracted are minus 4x. And then I bring this 2 down. And I repeat the process. I'll do it with purple. What do I need to multiply this term by in order to make it the same as that term? 2. So I'm going to multiply by plus 2. And then you multiply them and you write them on this line in the appropriate columns. So it's 4x squared plus 0x plus 2. Subtract. 0 minus 4x plus 0. And the result is that I can rewrite my original rational expression as the quotient all on its own plus the remainder, which is a polynomial, divided by the original divisor. And if you want, we'll call this f of x. If you want, we can test it. Test at number 2. So that's 8 times 2 to the 3 plus 4 times 2 to the 2 plus 2 divided by 2 times 2 squared plus 1. I'll evaluate that on my calculator. That's 82 divided by 2 times 2 times 2 plus 1, 9. And on the right hand side, when I stick a 2 in, you get 2 plus 2 plus minus 4 times 2 over 2 times 2 squared plus 1. So that is 10 minus 8 over 9. I'll evaluate this on my calculator. 82 divided by 9 is 9.1111. And this is 10 minus 8 divided by 9, 9.1111. So it's the same. Okay. So, long division is a wonderful algorithm. It puts together a lot of ideas that we've been talking about before, And it also provides us with a way of writing a rational that looks like this, an improper rational, as a mixed expression. The same way long division lets us write a an improper fraction as a mixed fraction. Let's review the various concepts. Usually you're introduced to the division algorithm as being, you put in a pair of numbers. So you put in the divisor and dividend. So you divide the dividend by the divisor, and then you get out a quotient and a remainder, right? And we can write this relationship in shorthand using the division symbols, or we can use it with like fractions. But what talking about where the long division algorithm comes from tells you is that there isn't just a division relationship between these four numbers. There's also a multiplication relationship between these four numbers, where the divisor times the quotient, if I multiply the division times the quotient and then add the remainder to it, you get your original total number back. So we can think of these four different numbers as being in a complicated relationship that we can either express in terms of multiplication or that we can express in division. And that was a huge helpful thing when we started talking about rationals, because you can express a rational in terms of two polynomials. One of them is the divisor, one of them is the dividend. Or you can express the rational in terms of a polynomial, the quotient, plus the divisor the remainder divided by the divisor. And these two together give you the overall rational expression. You're rewriting the rational expression in the same way. There's another medicine wheel. Numerator and denominator, that's another way of saying divisor and dividend, right? But there's also a relationship between the two. And we can express that relationship either as an improper, possibly improper rational expression, or as a polynomial plus a rational expression. So the long and the short of it is we can use this algorithm to rewrite a rational expression as a different rational expression. And sometimes that's a helpful thing. Sometimes it tells you a lot about what's going on. So that's it for this video. These particular things are pretty helpful if you get some practice in. So come to class and I'll give you some practice.